Good morning, everyone. Sorry, it's running a little bit late today. I'm only 1 minute behind, so it's not too bad. Here's my lecturer in charge. As usual, she's looking for somewhere warm to sit, so hanging out here for the moment. How's everyone going at the moment? We have had a reasonably big week with 1511. Let me just organize my camera a little bit. What did you have this week? This week we released an assignment, and we had the bonus live stream yesterday as well, so it's been pretty busy. Lots of little things going on. If you're confused at all about anything in the assignment, or you're unsure about where to get started and things, the recording of the bonus live stream is on my YouTube channel. I haven't yet uploaded it to Echo 360, where I know a lot of people are getting the lecture material from there anyway. But that will be up very soon. I will probably upload both the live stream and this lecture this afternoon when I get some time. Giro-chan was asking, "You're curious, what is the story behind Chicken's name?" So, Chicken's called that because, you know when cats, when they sit down, and then, like, they just kind of curl themselves up a bit, they look kind of like if you put, like, a roast chicken on the ground, they've got the same shape. That's how she ended up with that name. So, it's a very, very funny, silly name, but I think that, having cute, silly names for your cats is just a fun thing to do. Okay, so, let's get into what we're talking about today. Today is part 3 of our series on linked lists. So, up until this point, on linked lists, on Tuesday, we recapped the kind of starting information about linked lists, like what they were, and the structs, and everything like that, and we did insertion into linked lists. And we also added to that the ability to loop through a list and stop when you find a certain condition. So the condition that we were going for was a notion of alphabetical ordering. It wasn't exact alphabetical ordering because all we were using was strcomp, string compare. I think if I wanted to do genuine alphabetical ordering, I would write my own function that maybe converted all the strings to upper or lowercase and then did a string compare on them, or something like that, something along those lines. But this was good enough for our purposes because we were just looking for a quick test to show the fact that we could loop through a list, stop at a certain point, and save the pointer for where we were. And that way what we can do is we can save a marker into the list at a certain point and say, okay, we're going to insert after this marker. And so that got us to the point where we had a Battle Royale able to put together a list of players from the very beginning and know that once you'd finished adding all the players to the roster of players, as it were, the whole roster would be in alphabetical order. We're still a ways off what we need for this to function as a roster for an actual game. So one of the things about this particular genre of games, Battle Royale, is that usually you put 100 people in together, and then they get picked off one by different means of the game, depends on which game it is, until only one person is left, and that person is crowned the winner. And so what we want today is to learn about the ability to remove items from a linked list. And then we're going to find ways to remove items from a linked list. The one we're probably going to go for is something where we type in someone's name and then we look for that person in the list and then we remove that person. But there are other ideas of what we could do. There's one which I might get a chance to talk about, but I very much doubt it because I want to spend time on the proper working of linked lists. But there's a way to do it where you can actually generate a random number, and there's a C standard library for generating random numbers, and I could make a random number and pick a random person from the list and remove them. Probably won't get a chance to go through that one, but I'll leave it there, and I have some notes in the slides about what functions you can look up to be able to do that if you want to. I think what was I going to say? You could do something with a loop. Actually, I won't go into it too much, but you could do something with a loop that goes a specific number of times into the linked list and then remove something there. But I'll only look at it today if we have time, because it's not something that is really necessary or core to the course. But a lot of people like to look at random number generators because they're reasonably useful for things. When I was doing all that stuff with dice at the beginning of the course, everyone was like, oh, could you randomly generate stuff? And I was like, not until I've taught you about libraries and calling functions and things like that. And so now you know. But there's kind of, in a sense, it's not really that difficult. You could look it up yourself, as opposed to, I think the time we want to spend is on removal from linked lists. So on to what we're doing today. Excuse me, sorry about that. We're going to look at how to remove something from a linked list, and this isn't just for the Battle Royale, this is generically how we remove something from a linked list, and how we free memory. And then we're going to look at actually playing this game. So we're going to look at a sequence of things that you can do to remove people from the list one at a time, and then end when there's only one player remaining. So a bit of a recap of what we were doing previously. In fact, let me set us up for today. So if we recall, be not a bad idea, I think, at this point to have a look at what we had in the previous lecture, which was, that would have been lecture 13? I was just like, because I know we've got like 3 lectures on linked lists, and I forget which ones they are. I think it's 12, 13, and 14. I think I made one for 14 already. We can always find out when we look at this one. Creating linked lists, looping through the list, printing out the names. No, this was the original. This was the first one. So the first one was 13. And then the second one, the one that I'm looking for, is the one where we're currently up to, is 14. Let's see what my comment is. Part 2, inserting into the linked list, also finding specific insertion points and inserting into an ordered list. Okay, so going back through what we were doing, we've got our player struct, which has their name and a link to another player. That's a standard linked list kind of structure. The part that is the standard linked list is the fact that it has a pointer to its own type, which means it can link up to another node in the list. So the things we added in the second lecture was insert after, which was a generic function that could insert after any position in the list. So you say, I give you a position, and then you can insert an element after that element. And then we had insert alpha, which was going to use insert after as well as a loop to find out alphabetically where something should go in a list. Now, it's important to know that insert alpha, like you're going to hear a lot when you're talking about programming and stuff, people are going to talk about things called sorting algorithms. Sorting algorithms will take a list or an array that isn't in order and then put it into order. And there's a lot of work in those, to the point where we would probably, if we were going to do them in 1511, I'd want to spend 2 weeks on them or something like that. So obviously there's no time for that. But eventually you'll hear about those. This isn't a sorting algorithm. This is just, if the list is sorted, we can add something to the list that that goes in the right position. So we can assume that a list with no elements in it is sorted because there's no elements, so it can't be wrong. And a list with one element in it is also sorted because there's no way that a single element can be out of order. So if we assume that, then we can always insert into a list alphabetically, because we start with nothing, then we add one, and then we add another, and we'll put that in alphabetically, and then we add another one in, put that in alphabetically, so we know that our list is always going to be alphabetically ordered if we use this, so we don't have to use more complicated algorithms to make sure it's in order. So if we have a look at these, insert after, says we're going to make a new player. So what we're starting to see now is this cascading use of functions. We have a create player function here. We're using the create player function in the insert function. And then when we do the alphabetical insertion, we're using the insert function. So when we call insert alpha, it calls insert after, and insert after calls create player. So we have this chain of functions going on here, and there's no theoretical limit to how many functions you can call in other functions. I mean, eventually it would have to be a lot of functions, but eventually you could hit a memory limit by using so many functions that each function, when it gets called, takes up a little piece of memory to save what instructions or what variables it's going to use, right? But to hit that limit, you would have to, I don't know how many million functions you would have to call in a row without returning from any of them to hit that limit. But it's not a limit we think about. It's not really a functional thing that's going to stop us from doing things. So the idea that we can call a function that calls another function that calls another function, totally doable. We're going to do that. We're going to do that a lot, really. So I like this example because it gets to show us doing that. So insert after, just if the insert position is null, then you're the new list. So we're going to return the thing that was created. If you're not inserting into a null position, then you're inserting somewhere in a list that already exists. So you join up to that list. Let me see if I have some slides. You join up to the list. Oh, wait. No. This is the finding. Oh, no, I didn't put the slide. You can always go back in the lectures to find the diagrams for inserting. I was wondering if I had actually put all the diagrams in, but I didn't, because I think I've put the insertion diagrams in previously anyway. So what we do is we take our next pointer and copy the next pointer that was before us, and then we take the node that was before us and get its next pointer to point at us. So this is the new one, and two things have to change. Its next pointer has to aim at the rest of the list, and the previous part of the list then has to point at the new one created, and that links it all back up, and we're nice like that. So that's our insert after. And then our insert alpha is just doing something where it tracks two pointers. This one I do have a diagram for, because this is the most recent thing we can do. So it tracks two pointers, the pointer that it's looping and this previous pointer that says, what is the node just before we stop the loop. So we stop the loop once, in this case, once D is before something alphabetically. If it's after anything alphabetically and we need to go past those objects, insert in between. So if the loop stops here, we'll have a pointer to this one, and we say insert after this node, and then we will insert the new node after this node, and it'll end up in between these two here. So my insert after is just going to loop until my string compare becomes equal or lower. So equal or lower means I'm happy if I get two strings that are the same, that I'm going to insert before the string that was in there already that had the same name. I mean, when they've got exactly the same name, it's a bit ambiguous what we're going to do with alphabetical ordering, so it's not super important. Shai was saying, and I can only do this in that particular order. I think that you were talking about changing these pointers around for insertion. Yeah, the order is actually really important, because note that insert position next happens in both of these. So if I did these in the other order, things would get really, really interesting. Because if I said insert positions next points at myself, and then I say my next points at insert position next, I would say that my next points at myself, and then I've got a loop, which would be really bad. Okay, let's this is a good one to draw, because it's really obvious once you draw this. So let's say That's a giant linked list node for no real reason. So I've got my nodes here. This is the one I'm trying to insert. So if I do these in order, it's pretty simple. Next player, new player next is equal to insert position next. So this one is insert pos, and this one here is the new one. So these are the only two things that I know about at this point. So if I say new next is equal to insert position next, then the new next copies the insert position next, points at the same object. And then the insert position next points at the new one, which means it will no longer point here. And instead it will point here. And then as you can see, we get a nice linked list. Let's look at what happens if we do it in the wrong order. So if we did this in the wrong order, and we took the second command first, insert position next points at the new player. So we take this, and we point it at the new player. At this point, we've already got a problem, because this node here, we no longer know the address of this node here. So this node and all the things that chain off it are now a giant memory leak because we've lost it. The other funny thing is if we did these in the wrong order, so insert position next is pointed at new player, and then new player next is pointed at insert position next. So new player next points at insert position next is pointing at this node. So we end up with this. And then we're in worlds of trouble here. You may find this in your assignment because when you're working your assignment code, mistakes like this can happen. And they're pretty funny because the next time you try to loop through the list, you go from this one to this one, you go from this one to this one, from this one to this one, and then you've created an infinite loop. Even if all of your looping code is perfect, you created an infinite loop because of something else. This is why this comes at the end of the course, not at the beginning of the course, because if I threw this in like week 2 or 3, then I don't know. I'm not sure what the highest level of dropout rate possible is in a course at UNSW, but I could potentially achieve that if I started with linked lists before teaching, like, variables and arrays and things. And like I made sure that you had a bit of time with pointers before we actually went into this kind of level of using them. Okay, so we're here and then we'll keep doing this. So we're doubly bad here because, for one, this linked list never ends. So we'll be looping like crazy. The other thing is we've got a memory leak here because we've lost the rest of the list. We didn't connect it up. So yeah, order is super important because if you're going to change this pointer, you want to only change this pointer after you've made sure that this node connects up to the rest of the list. And Sean's saying, imagine how many infinite loops would have been created if this was in week 2. Yeah. So it's good and bad, right? It's like, on one thing you're like, oh my god, this is like really full on to understand all this theoretical stuff. But on the other hand, you're actually at a point where you potentially can. And I'm not saying that everyone needs to understand this immediately, right? This is like pretty full on what we're talking about here. Theoretically, there's a lot to think about. So this kind of diagram and stuff is something you might want to go back and think about, draw yourself, think about how your code interacts with the diagram. But what I like is that, we've only been programming now, a lot of people in the course have only been programming now for 2 months, but you're already getting to the point where this is viable. I'm not saying that you have to understand this right now as I'm talking about it, because it's hard. You may want to go back over it and spend some time with it, but it is viable that you will understand this. So I like that. I like seeing everyone's progression as we go through things. And Raymond's saying, what sort of effect will a memory leak have? It depends on how much of this there is. If we use up so much memory that my operating system will not give me any more memory, the entire program will get killed. As William's saying there, we showed an example of this when we were talking about memory allocation. The entire program will just stop. The smaller ramification of this is if a lot of programs leak memory like this and they keep running for a long time, you'll find that your computer will just start slowing down because there won't be much memory available, and it's harder to find memory to allocate to programs and things like that. What a computer often does when it hits that position is sometimes it'll say, I'm going to let you keep using memory. But what I'm going to do is, because there's not enough physical memory on your computer available to keep doing things, it's going to move things onto the hard drive. So it's going to move things that were in memory onto the hard drive. The hard drive is, ballpark figure here, roughly 1,000 times slower than the memory. And so if you're moving into something that's 1,000 times slower, suddenly everything that you expected to be able to read and write to memory is doing it 1,000 times slower, because it's having to move stuff off the hard drive first before it can work with it. And that way you get computers that start to really, really slow down when they're running out of memory. Yeah. Miguel said, when I leave iTunes open overnight, it gets up to 8 GB of memory usage on my laptop. So I'm going to guess that iTunes has a memory leak. I don't know. It might not even be a memory leak. Some applications just have aggressive memory usage. So there are some things on certain programs, like say Google Chrome, that try to keep everything in memory that they don't necessarily need in memory. So the more tabs you have open, the more memory Google Chrome will try to use, even if it doesn't really need them. But it will make things faster if you keep switching between tabs. And so certain programs just eat memory. They're not leaking, because they'll give it back if you close the program. But they will use as much as they can, and you'll find the rest of your computer slowing down when it's all being used. Paraham said like Chrome, right? Yeah, that's the example that I know a lot of people know, because Google Chrome's a very common one for that. Okay, so this is our insertion and some possible problems with our insertion. So insert alpha just loops through to find the right position, and then it calls insert after. It is careful also to make sure that if insert alpha was trying to insert at the start of the list, it changes what the head of the list is and returns the new head of the list. So what we want to do is every time we call insert alpha, we want to assign the head to the result of insert alpha, just in case the head of the list has changed when then we get given back. Every kilobyte of memory for Microsoft Flight Simulator. Early days of Microsoft Flight Simulator was actually measuring memory in kilobytes as well. Okay, so that's where we're up to at the moment, inserting alphabetically. So now we want to look at removing a player. So the goal that we have here is to remove a specific player given their name. So we're going to assume that the rest of the game is running somewhere else, and then when the rest of the game detects that someone's been knocked out, so either in the Battle Royale, the ground you're working with shrinks, and if you get caught outside, you get knocked out. So that might happen, and the game will tell us the name of the person, or two people get in a fight in the game, and one person loses that fight. And so we're assuming that there's something else. There's another program that's going to tell us the name of the person that gets knocked out. For us here, we're going to type it in. It's easier for us to just do it this way. But we want to split this up into parts, right? To remove a specific player given their name, we're probably going to want something that removes a player first, and then something that can find a player given their name. So we'll probably remove a player based on a pointer to that player, maybe, and then something else that finds a player given their name. Although we may be able to do this all in one. Let's see. I think I've got a plan to do two functions here. So let's look at what it means to remove something from a linked list. So here's my diagrams that I've been using, same kind of layout. We've got a first player, second player, and a third player. Oh, this is my old example. So before I changed everything to Avatar: The Last Airbender, I had been re-watching Dragon Ball, the original Dragon Ball, like the 1970s? Do I want to say 1970s or early 80s? The really old one, before Dragon Ball Z, before I got super famous. And so I had the Dragon Ball characters in here for this one. And Tom was involved in this one as the subject admin, which is quite funny because I think I removed Tom from this list. So first player, second player, third player here. And I'm going to remove the second player from the list. So in order to remove something from the list, I have to make sure that the list is consistent while that thing is going to be removed. So if this node's going to be removed, the rest of the list must be consistent. So the first player bypasses the second player here. And this can be any node that's the one that's before the thing that's going to be removed, has to bypass it by moving its next pointer. So what it's going to do this is actually copy the removing node's next pointer and say, since you're not going to be around anymore and I need to connect to the rest of the list, I'm going to copy your next pointer, and that skips over you. Then we now have this node that's floating around on its own and is no longer necessary for the list. So what we're going to do is free the memory from that node. So we're going to make sure that if we remove a node from the list, we give its memory back to the system. We don't want to have it floating around and us not having a pointer to it, because if we ever have allocated memory and we don't maintain a pointer to it, that's another memory leak, right? We're not going to remember where it is, so we're not going to be able to free it, nor are we going to be able to use it. So we'll free this node, and then once we've done this, we have a perfectly formed linked list here. Nodes, pointers between nodes, pointer at the end pointing at null, and this memory is freed, which means this chunk of memory here I can now reuse for other parts of the program. Ooh, okay. Break time was really early there. I think I did the break time based on the number of slides. But most of those were recap slides, which I go through faster, so we're definitely not going to take the break now. Jamie's asking, can specific memory be reallocated? Memory can be reallocated, but you can't ask for a specific piece of memory from the computer. So when I say to my operating system, please give me a piece of memory, it's just going to look for free memory. So if I ask for a node's worth of memory, it might give me a chunk over here. This is not to scale or anything, but like it could give me this chunk over here, it could give me this chunk here, or over here. It depends where it thinks the next free piece of memory is. The way this stuff is usually laid out is it's actually much more compact than these diagrams. Everything's right next to each other. So everything's packed in really tight. When you first initialize things, but if you free something, it might just pop out from the middle there, and then your operating system will look through looking for the next free piece of memory, and if that's the right size, maybe, no guarantees, but maybe the next node that you allocate will be exactly where this one left, because there's an open chunk of memory that's exactly the right size. But in terms of grabbing an exactly specific piece of memory and using it, that's generally not possible. There are ways of doing it though. There are interesting things that people do when they're super optimizing their programs, is they actually allocate a massive block of memory. This is very much a computer games thing. Computer games tend to do this to make stuff run extraordinarily fast, because in computer games we're in a real-time world where we want to get a whole lot of work done in a 60th of a second. So we start doing what you could nearly consider to be very silly things in terms of trying to manage stuff in order to maintain speed. So what you could do is you could allocate, say, 4 gigabytes of memory, and say, I put a node here, and I put the next node next to it, and the next node next to it, and things. And when I remove a node, and I allocate a new node, I put it exactly where the other one was before, so that anytime I grab memory for the linked list, I'm going to grab a bunch of linked list nodes together, rather than grabbing a piece of memory from a linked list node and a piece of memory for something else and some code for the program and things. So what we have is, if everything that is going to be used together is next to each other in memory, it makes your memory usage faster, because you don't have to jump around memory looking for things. And as Trent says, Mark, did you mean 144th of a second? Yes, maybe I do. Yeah, I know. I also have now gone back to being a 100 frames per second snob, that I require my games to go faster than that. It's quite funny. I started off gaming in the era where 100 frames per second was what we were aiming for all the time, because we had older monitors that didn't have the 60 frames limit that early LCDs have, and now our LCD panels have 144 frames, and we get to the point where we can get that buttery smooth frame rate now, where you can't really tell that something is several images in a row. Oh, Miguel, if you want a screen that has more than 60 frames per second, there are old cathode ray tube screens you can get. They've got a massive 640 by 480 resolution, but they will run at more than 100 frames per second. And Shai said, you're accessing this lecture from your Samsung smart fridge. That would work, right? You can watch YouTube on a fridge nowadays, right? Anyway, let's move on. So, I was going to have break time there because there's a split between talking about code and actually writing code. But what we're going to do is actually start coding this. We might actually, in that case, get up to the random stuff if I'm this far ahead of time that I think I am. Okay, so finding the right player means looping until we find the right player. I think that... Yeah, I think that we had to bundle this into a single function rather than having a separate remove using a pointer, because it sort of bundles together. So let's have a look at making this function now. So the interesting thing that you're going to see is every time I make a function that is going to change a linked list, I'm always going to return a pointer to a node in that linked list. And this is because anytime I'm guaranteeing to make a change in a linked list, I am not able to guarantee that the head of the linked list is the same. And in my main, the only access I have to the linked list is via the head. So via the pointer to the first node in the list. So if I'm going to change the list in some way, I always need to give back what the new head is. So for example, if I were to remove the head of the list, if I'm going to remove the head of the list, then I need to return a pointer to what is the new head of the list, which will probably be the second element in the list. Likewise, previously, if I'm going to insert at the head of the list, I need to give back a pointer to the new head of the list. So none of the insert and remove functions here, I can't do any of those without giving back the new head of the list. You may notice that we've gotten around that in a very, very smart way in the assignment. Because the assignment says, I will give you a struct that maintains access to the pointer to the head of the list. And so I say, I could just give you a struct that says, for example, the library struct in the assignment. And the library struct maintains the pointer to the head of the list. So you can change that in the library struct without changing the library itself. So you're only changing one element of the library. One field, sorry, in the library. And so that's really nice, because then you can just pass the library to something and then not need any output. So that's a nicer way of doing it. That we'll do a bit more with that next week. I do have one example next week with a linked list that will use that. But you can also see the example in your assignment where you don't need as much fiddling around as we have in the basic example we're doing here. So a function is called remove player. And to remove the player from something, I'll need a pointer to the list itself to remove it. And then I will want the name of the player. So I was about to type in new name because these are all new names, but this isn't a creation or an insertion function, so it's going to need a better name than that. So I'm going to call it remName to be the name of the thing that's going to be removed. Alright, I will copy that. Oh, I'm just going to Control Z everything here because I just realized where I am. Okay, save that. I'm in lecture 14 here, but we're actually in lecture 15 now. Let me make sure. What are my numbers? No, this is lecture 14. Why? So, lecture 13. Have I messed up somewhere and skipped a number? We're in lecture 14, but when I looked at the code in lecture 13, it was like the first linked list code, and the second linked list code was here in lecture 14. Is there a number missing somewhere? Okay, doesn't matter. Okay, we're in lecture 14. It's fine. We will continue in lecture 14. And I know that if I've lost the code somewhere in between, it's fine because I uploaded it to WebCMS. We have our checkpoints everywhere in between. Yeah, and Jamie's got a good point there that maybe I skipped something because of Flex Week. Because I've got numbers for all of these. Which is weird because in Flex Week there was definitely things that didn't have code somewhere in here. Alright, doesn't matter. We've got our code and we're going to continue doing this demo. Now that I've thoroughly confused myself, I will put the proper stuff in here. Removing from the links list, specifically removing by finding a player by their name. Okay. I'll put this back in that I was started to put in. I think there's always this issue with me with when I create the folder for the lecture beforehand, and that's if I want to test out some code for the lecture beforehand, which I obviously did there. I end up in a situation where I can accidentally forget whether I've created something or not. Okay. Remove player. Oh, have a look at this issue that I've created here. These are in snake case and these are in camel case. This is really, really bad style that I'm switching in between two different styles here. It's like, this is what I do when I spread code over 3 weeks. Okay, what I'm going to do, I'm going to go to camel case because I think more stuff is in camel case at the moment, and I will I'll make some changes in a second. I'll show you how to do this thing called refactoring. So the list, and we had the name of the thing that we're going to remove. Okay, so we've got that. I'm surprised no one noticed. Did anyone notice that we were that I had inconsistent style here? Okay, so I'll show you what I can do to fix a lot of style at once, because we've got this one here. I'm going to press Control H here. If you don't have Control H or you forget what it is, you can go search and replace. So I'm going to take create player. Anytime I see create player, I'm going to replace it with this other create player, so I'm going to convert everything to camel case. I want to be careful, match entire word only, although it's unlikely that create player is going to be part of another word because it's a very specific phrase. If I say replace all, you've got to be careful with replace all, by the way. Often I will go through one at a time and replace them one at a time by going find and then replace, find and replace. But I know that this is such a unique word that it's likely to only be used in the function call. So there, create player, and now create player here, and every time it gets used, it's been renamed, right? So that's very nice. So I can go through and rename everything like that. So I can go insert after, replace all, insert pos. This is a very, very simple form of what we call refactoring, where we're moving our code around, but all we're actually changing is what it looks like. We're not actually changing any of the functionality of it. Sometimes you are also changing functionality. So refactoring could be considered taking a bunch of your code and putting into a function to say that, like, this is a better way for us to write this code, but the functionality of it isn't going to change. We find ourselves doing this a lot with our code, especially if we end up in a situation with our code that we find it too hard to read or too hard to modify. We may end up going through our code and saying, no, I want to rebuild this code so that it reads nicer, and I could go through and refactor all of it. So that's most of my snake case now removed. and replaced with camel case. Wait, there's one here. When you do it for a variable that's inside a function, be more careful. I'm not being super careful here because I think that even if it was somewhere else, it should be renamed like that. Okay. There's this one. Right. I could compile this now to check my syntax, but I know I have an unfinished function here, so I may need to at least get this started first. If I want to, I could just make sure that this function is legal. So I could say, if you want to point it back and I give you null, then it's at least going to work. Even if it's never going to get called, it's still going to get compiled and say it didn't have a return value. So I may just compile this now, just to be sure. I'm going to reset my terminal. Right. Should have been a dead giveaway that Lecture 14 was new, because there's no compilation here. So this program's never been compiled in this directory because I don't have the running program. That should have told me that I was in the right directory, but I second guessed myself. Okay, just going to call it Battle. All right, good start. We're syntactically correct. In case you want to look at it, we can run it. And so this was the series of insertions. If you weren't here for the Q&A afterwards, last time I added in a print after each insertion so that people could see that every new element that came into the list was getting put in the right place. Girashan's saying, yeah, if you use VS Code, there's a few tricks and things. I don't tend to use VS Code to teach the course because I want to keep us in the simplest possible setup that people can use if they've never seen any other kind of programming things before. But if you're interested, there are some resources within CSE. One of the subject admins put together a whole bunch of resources for how to do the same thing we're doing now within a program called VS Code, which is called Visual Studio Code. It's made by Microsoft, and it's one of the what we consider one of the professional programming environments. We don't usually use it when people are starting out because it's a little bit more complicated. But once you're actually on a roll and thinking about programming, you can convert to using that reasonably easily. Gira-chan, but real programs use Vim. Vim is like one of those things that people talk about in the programming world that can get you really fast on a keyboard. It's a text editor where you'll never use a mouse. You just do everything on the keyboard, and so it's potentially a lot faster. It just has a massive learning curve to get it right with all the commands. And so some people use it, some people are great with it and use it a lot. Some people never touch it for their entire lives, and they're highly successful programmers who never use it. So there's always this back and forth about whether people are going to use it or not. Yeah, and Gira-chan, I can 100% understand that typing in VLab would be hard from the US because you've got a 200 millisecond return time on things. For people in Sydney, VLab's probably a bit easier. Okay, and Shai is saying VS Code has dark mode. I wonder if... No, I'm not going to waste time in the lecture. I think that gedit might have it as well. Okay, now that we've fixed up that style issue that I had, and it's very hard for me to continue while seeing that style issue is there, we will now... I don't know if you heard that. Someone's just honking at people outside my place. Let's put together the remove player. So if I'm thinking I'm going to do all of remove player in one function, I want to be careful with how I'm laying this out. So find the player to remove. That's going to be loop through the list, maintaining a previous pointer. Stop when you find a name match. Oops. Name match. Okay. So I know that that's going to be the first thing, and it's going to be really, really similar to this. So we loop through, and we stop when we see something that's after us in the alphabet. This isn't going to be after, this is going to be stop when this name matches a name in a node. So, if we're going to do that, we're going to use a really, really similar setup, because we're going to want our previous and our current. We want the previous and the current because of the following theoretical situation. Here we're removing the second node, and we notice that when we remove the second node, we need to make changes to the node that was before it. If we need to make changes to the node that was before it, that means that we need access to this node. So that means that when we're looping through, we're going to have to do the same thing with a previous pointer as well as the current pointer. So let's do that. We're going to set up our player pointers. So first player pointer is previous. If we're going from the start of the list, then the previous starts off as null because there can't be anything before the first element in the list. And the current will be equal to the head of the list, the first item in the list. As we've done before, we don't want to just use the head of the list. We had this question, I think, on Tuesday, just in case we're going to need that again. If we need to rejoin these things up, or we need to return the head of the list, we need to at least keep track of where the old head of the list was. So if we have a pointer that's going to move through the list, we'll make a new one for this one. If we didn't have to return the head of the list, we could move that pointer. But I think most of the time, if we're going to do something like a removal, we still want to know where the head of the list was. Okay, we're now going to loop through the list. This comment's actually going to go here, I guess. I mean, a lot of these comments, which are my remember what you were supposed to do in this function, I'm probably going to delete them and change them to comments that explain things afterwards. But I know I'm going to loop through a linked list, which means I'm going to have the standard linked list looping setup, and I'll make that setup before I do anything else. Okay, so I know that if I don't do anything else with this, I know that the current pointer will move through the list one node at a time until it goes off the end of the list and points at null, and then it will finish. So I know that no matter what happens, well, assuming I haven't done this, assuming I've built my list correctly, this will loop through the end of the list and stop. So I've sort of guaranteed myself against the mistake of an infinite loop here by setting up my loop in advance. And I know that I'm moving the previous pointer through my list as well. So every time I move through the list, what I'm going to do is I'm going to take my previous pointer, I'm going to match up the current pointer, and then I'm going to move the current pointer along. And then I'll match up the previous pointer and move the current pointer along. So every time we finish the loop, the current pointer's moved on, the previous pointer is exactly where the current pointer had been. So my iteration here is not just moving one pointer, it's moving another one as well. So previous moves to where the current was, and then current moves to its next. So every time we finish the loop, we have two pointers that are next to each other, and the previous is actually the kind of important one. That's the one that we're going to be using later. But the current is the one that we have to move along to test things. So, what is the test that we want to happen? I'm going to use an AND here because I want either one of these conditions to cause the loop to stop. So if either one of these conditions fails, the loop will stop. And so we want the loop to stop anytime we find a matching string. So strcomp, and if we remember string compare, I love how it's like remember, and I say remember, but what I actually mean by remember is I'm using the collective memory of the human race rather than my own. So the collective memory of the human race is obviously collected in Google, and all I did was just hit the top item in the search. So I didn't even know, but it says C programming. C strcomp compares two strings. The first character of the two strings is equal. Next character of the two strings are compared, etc. until end of file. Returns 0 if both strings are identical. Negative if the value of the first is less than the second. Positive if the value of the first is greater than the second. So both strings are equal, it will be 0. So that's the one we're looking for. Thank you, memory. So string compare, the two things we're comparing are the name of the thing that we wanted to remove and the name that our current pointer is aimed at. So current name. Cool thing about this, this works even if I give it an empty list. So even if current is null. So what if I say remove a player from an empty list? Oh, already there's a problem there. Because if there is an empty list and I'm saying I'm telling it to remove something, then I've must have made a mistake somewhere else. Because there can't be anyone to remove if there's no one there. But still, this while loop is really smart. Because it says, if the current is not null, then you can continue. But if the current is null, then the while loop will end. And because this is an and fails if either of these things fails. So this one will be tested first, and if it fails, this one will never run. Which means if at any point current is null, and current name is invalid, like that would cause an error if we read current name, this part of the and will never run, so this is actually safe. I'll show you what happens if we flip this, and I were to do this in this order instead, I would have a problem now. Because if I get to the end of the loop, for example, and current is null, I will test current name even if current is null. And then I will test if it's null afterwards here. So this is bad. Because actually most of the time, well not most of the time, a lot of the time when we run this loop, current will be equal to null at the end of the loop. Which means that this will cause an error. But if I checked if current was null first before accessing the current name, so this order in the one line actually makes a difference. If I check this whether it's null first, then I won't cause this failure. So I will cut that out and put this here. And this is a safer version of that while loop test, because we will only check for a name in current if we know that it's not null. Okay, so string compare has to be tested against the 0. So I need to be careful about what's going on here. I want the while loop to keep moving if it hasn't found the person, and stop moving if it has found the person. So the condition I'm asking here is, what condition do I keep moving? So I keep moving if I have not found a match. So the while loop will keep running if it hasn't reached the end, and also if it hasn't found a match. When it finds a match, it stops. So here, stop when you find a match. So you'll stop if this equals 0. So when we're done with this, previous will now point at, oh no, not previous. Current will now point at the node that matched or null. So we have two conditions. One condition is that we found what we were looking for in the list, in which case current will point at that node. Or we did not find what we were looking at in the list, so this was not the stopping case that actually stopped the list, but this was what stopped the list. So if I make a typo or something, so I look for ang, and I put 3 A's in by accident, it's going to loop through the whole list not finding him, and then current will be pointed at null. So if current's pointed at null, it means we didn't find the person. Okay, so what we now want to do is, using previous, remove current from the list. We're going to do this exactly this way, where we say, first thing that I want to do is I want to use the previous next pointer and skip over the current. So I'm going to say previous is next is a copy of current's next. That's this bit. So I go from here, and I've identified this one as the current, and this one as the previous, and I say this is next, skips this one by saying, I'm going to copy your next, so I'm going to point first player at third player here. That's this line of code. That does this, and then after that we're going to free the second player. So we're going to free the current, and at that point we can return the head of the list. Now we need to be a little bit careful here, right? What are we talking about in chat? Oh no, we're just talking about bright and dark color schemes for things. I think. Yeah, I think there was a whole conversation there about bright and dark color schemes. Okay. So what we've done here is I have removed the current from the list using the previous next pointer. So the removal code is very simple. Again, it's just like the insertion code. It's very simple, but the ramifications of it are quite complicated. The theory behind what we're doing here is complicated because we're changing the same pointer multiple times and things. So we've got to be a bit careful that we know what we're doing before we write this small amount of code. The other things that we need to think about here is there are many issues that could come up here. So what if previous is null? And what if current is null? Both of these can be null. So we've seen that here, current can either point at the node that matched or null. We also see that previous started as null. So we have two possible issues here, and they're different depending on what's going on, and we need to check for both. So let's be careful with what we're doing. So if previous is null, the node we're removing is the head of the list. So if we're removing the head of the list, things are different because there's no previous that we can change. I'm actually going to put this one above because it's related to this while loop. If current is null, so if current is null, it means we got all the way through this while loop, which means we went through every item in the list and we went off the end of the list. That means we didn't find a match if we made it off the end of the list. If current is null, we looped all the way through the list and didn't find a match. So we have two things that are going on here. And we need to check for both of these being null. So I can say, let's do the first one first. If current is null, then something's going to happen. So if current is null, let's put this inside here. And I don't need to say if current is null because I've just said if current is null there. This says we looped all the way through the list and didn't find a match. So if we've gotten all the way through the list and we didn't find a match, that means we have we've not found what we were looking for, which means we will not remove anything. Don't remove anything. This is nearly an if statement that has nothing, because we're literally not going to do anything here. So we're actually only going to take action if the current was not null, which we could put in an else statement here. But if we have an if statement that's empty, then maybe we could just flip this. So I can say if current is not null, then we're going to continue and do things. So this is, we found a match, so we'll remove it. And I could nearly say here, else, do nothing. Oh, actually, I won't bother. I'll just say that if we found a match, we'll remove it. And then that there are multiple conditions on finding a match. one of those conditions is if previous is null, it's the head of the list that we're removing. Just gonna get a bit more space and make sure I can see where my 80 character limit there is. If previous is null, we're removing the head of the list, otherwise we're not removing the head of the list. So let's check for that in here. So the reason I'm checking for previous is null inside this is if current was null, then I know that I'm doing nothing. If current is null, then I know that all I'm going to do is skip over all of this code, because all the code for removing is going to go in here. And if current was null, then there's nothing to remove. We would probably skip straight to returning something. I'm going to assume that we'd return list, because if we have not made any changes to this list, we've not changed the head of the list, we'd just give it back. Which means if the previous was null, let me put this in here, because I'm now putting in these conditions. So if previous is null, we're removing the head of the list. Else, we're removing another element of the list. So in here, in this condition, we know that we're definitely removing something because current wasn't null, which means we found a match. And we know that previous wasn't null, which means we're not removing the first element of the list, so we can use our sort of generic removal in here, which is this. She'll love my indenting there. Let's fix that up. Sometimes if you cut and paste exactly the wrong stuff, you get an interesting result. Okay, we don't need that comment anymore. And look, we've got 2 return lists here. We definitely don't want 2 of those. Completely unnecessary. And I'll move my brackets back up to here. Okay, so now we've got a set of conditions. If we found a match, we will remove it. So if the current is not null, we will remove something. If the current is null, we'll skip over all of that and just give back the list. Because it's like, I couldn't find anything to remove. I'll just give you back the list you gave me. Then if we are definitely going to remove something, we will check if it's the first element of the list or not. So if the node we're removing is the head of the list, we'll have to do something here to do. This bit isn't finished. That's not a great comment, by the way. Removal of the head of the list. There you go. That's much better. I just laugh. It would be really funny because every now and then, very rarely, but every now and then I'll go through and like see people's auto tests midway through because like your code is saved, or see people's submissions partway through because they're like, I just need to back this up, and the to-do is like, this isn't working. It's like, okay, I'm going to try to be better with the to-do here and say, okay, removal of header list is something you have to do. Otherwise, we're removing another element of the list. So we're actually nearly done here. We've found the element, and then we've tested all the different conditions we might do for removal. And we do have the correct, well, we think, we haven't tested it, but we've got code for removing some element of the list. Shy is saying stage 3 is going to be near identical to this code, I reckon. Well, there is a thing that happens in university subjects where one will teach students particular things and then ask students to be able to do those things in an assignment. So it's not that far-fetched that a significant portion of people's assignment code will be this code that I'm writing now modified in a particular way to work in the assignment. I'm okay with that, right? Because I'm okay with you using the code that I've taught you to complete the assessment tasks, because it means at least this is going through your head and processing. You will have to decide exactly how different this is from what you're doing. So I'm teaching you the generic capability to do something, and then I'm going to ask you to put it into a particular context. So yeah, I'm okay if this is close, you know. Giro-chan, for every program I just need to write, I did stuff and it somehow works. That's all your comments. Dan said there's no semicolon on line 148. You are correct. That would have been interesting. Okay, I'm going to pause here, which is why I've got the to-do here, because we're at 12:06. So we're going to take a break. So I went a little bit further than I was going to in the break, but I wanted to talk a little bit about some things that you can use. We're not specifically teaching them in 1511, but these are things that some people use, and we're using tools like this in the background. Like, your assignment was worked on by 1, 2, 3, 4, 5 people, I think, in the background, and so we were all using something like a tool like Git to make sure that we could all make changes to the same thing. We're all remote at the moment, so we're all in our own homes, so we're not in the same physical location talking to each other and things. So when we make changes to the same files, a program like Git can actually merge all of our changes together into the files. Not only that, but these systems that are called source control, if you want to look them up, allow you to keep a chain of backups of your code as you've worked on it. So I suggest that having a look at these things eventually is a good idea. Getting a handle on how to use them is, I would consider, and I'm pretty sure a lot of other people would consider this to be a professional requirement. So this is something obviously not needed yet. Any of you who are going to be professional programmers, one does not become a professional programmer by doing just COMP1511. There's plenty of other things that you'll do, and then you'll get specific teaching about these. But I think it's worth it if you want to set this up. CSESOC often runs workshops on how to get these things set up, so very beginner level, so that you can either go to those or just look for videos for old ones. You can even go to CSESOC's Facebook and ask them about it, and people will have links to previous workshops that have been taught. One thing that I will say to you, just be careful, because you can get free student level repositories, which are at the professional level, but because you're a student, they'll give them to you for free to use. Just be careful that anything you upload there, unless you set up specifically, anything you upload there will be publicly available. So if you start working on assignment 2 and you make your own Git repo and you're really excited about all this stuff and you go, oh, cool, I'm going to start regularly backing up my assignment 2 to this. If your assignment 2 goes up there public, you could get a little knock later on from me or someone else saying that you're under investigation for plagiarism, because you can literally Google for assignment 2 COMP1511 and find your Git repo because it was public. So just be careful about that. So if you're going to have any accessible material, make it private so that it's not able to be used by someone else. You're probably going to have to keep that private for quite some time, because if we do reuse this assignment in like a year's time or something like that, we don't want your code floating around able to be used by other people. Yeah, but also Git's really good. I use GitHub. When I'm on Windows, I like SourceTree is a very nice graphical interface into GitHub. I was about to open it and show you, but I think if I open it and show you the recent commits, you'll see will all be like the building of the second assignment. So I don't want to show you just in case they give something away. Yeah. Miguel's saying GitHub might be private by default, so it might be okay. Yeah. And Girichan, you can use GitHub. You can use GitHub during and after the deadline as long as you don't make it private. The thing about after the deadline is that we kind of actually need these assignments to stay mostly private nearly permanently, because even if when we reuse the assignment, we will change the assignment when we reuse it, but even just having it out there means that if people look at your solution to the assignment and it's different from the current one, it'll actually confuse them even more. Not that I mind that much. If people are trying to cheat in the assignment and it confuses the hell out of them, then I'm kind of okay with it. It's like a little bit sneaky like that, but it's often better just to keep the accessible stuff private all the time. And then if you go for a job interview and you know some assignment stuff is stuff you want to show, you can make it public just for a short amount of time to show someone in a job interview and then flick it back to private afterwards. Anyway, let's take a break. It's 12:11 now by my clock, so we'll take 5 minutes. and it'll be 12:16 when we come back, and we will continue with our removal code, and we'll start testing it and rolling into the game and things like that. I'm back. I'm just laughing at the text chat that has happened during the break. People are talking about intentionally releasing bogus assignments on GitHub to screw with people who might be cheating with the assignments. And I said, please don't intentionally screw with future students. And then Giro-chan's response was, well, that just leaves current students. Please don't screw with current students either. It's all fun and games. But you know, when it comes down to it, if you feel like you need to look at other people's code, or you feel like you're so stuck with the assignment that that you can't find a way of doing it yourself, talk to tutors, because there's no cheating with tutors. You can show them all of your work, Ask them anything, and the tutors are trained to know how much they can tell you. So they will give you help that you can use that isn't considered cheating. So I think that's a much better way of getting around things. So tutors first port of call, it's really good. You can go to any lab. You don't have to just go to your own lab and your own tutor. You can actually go to any lab that you want to that's open at that particular time. So check it out via Moodle, the Blackboard Collaborate sessions. You'll see on WebCMS the timetable will also tell you about when all the labs are, especially let's say next week. Actually, this is the week after next, isn't it? So what are we? We're week 8. And it's due at the end of week 10. So in week 10, you could look for labs where the tutors aren't so busy, because there's a little bit of downtime in the labs. You may be able to get help there. There's also help sessions where you can talk to a tutor one-on-one as well. The wait time in help sessions is usually longer than in a lab. If you get lucky and turn up in a lab where the tutor's own students are already busy working on things. And then you can ask the forum about sort of general ideas of how to do things. Like you could ask on the forum how to remove something from a linked list, and you'll get some advice. But if you ask really specific assignment questions on the forum, you might get bounced to tutors instead for specific one-on-one help. But yeah, all of those things, if you're in a position where you think you need to look at other students' work, I'd say all of those things are better things to do. Because if you go and talk to a tutor about the assignment, nothing you say or do in that conversation is considered cheating. Well, unless you say something like, "Oh, I cheated off that other person," then the tutor's obviously has to say, "You probably shouldn't do that," right? But but anything else you do, you can ask them anything, and they will limit their answers so that they don't put you in a position of having cheated or anything like that. Yeah. Uditha is asking, regarding plagiarism, do we need to reference code from the lecture slides? No, you don't. If you do use something from outside the course, especially if it's something quite specific and you say, I learnt this from somewhere else. So let's say I wanted to use I'm trying to think of what techniques you could use. I can't think of anything that have specific names, but there could be other techniques that you might want to use that you've looked up online and you've learned from somewhere else. You can say, I learned this from such and such. You really only have to reference other things that you've learnt if it's if you've actually copy-pasted code. So if you've learnt the technique somewhere else and you're just using it, that's fine. So there's people that might be using a technique called recursion. Although I'm going to teach that later anyway, so it doesn't even matter. There's other ways of going through a linked list that you may have learnt the technique elsewhere and you've reapplied it here. That's not really that big a deal. I think it's only if you're specifically using code from elsewhere, then you do have to credit it. Because it's pretty bad if we, because the plagiarism testing stuff is going to look at all your code, and if it finds snippets of your code online somewhere, it's going to find a match. And then it's going to say, this is exactly the same code that's on this website. And then we see you don't credit it, and we're like, well, that's pretty bad, because that's someone else's work, and they should be credited for their work, because they put a lot of time and effort into it, right? So we want to get into the habit of, anytime we use something that someone else makes, we want to give them a shout out, right? We want to say to them, hey, you did great stuff. I used it. This is really cool. And so I'm going to tell people about the work that you did so they can look up your work and your other work like that. Gira-chan is asking if the weekly tests and labs are tested for plagiarism. The tests are, but the labs aren't. The labs aren't because we specifically want people to work in groups on that. So if I get 3 students literally handing in exactly the same code, especially if they're in the same tutorial in the lab, then I'm saying that's pretty good. That means people are doing pair programming or group programming and stuff like that, right? But the weekly tests and the assignments are individual. The exams also run under the same system. Okay, let's get back into it. So we're removing a player. Oh, they've got all the stuff here in the slides, but I don't think I'm going to go into the slides too much because I know that we're on our own track of what we're doing here. So I had this to do. So I'm removing people partway through the list. But I do want to see what I'm going to do if I'm removing the head of the list. So if I'm removing the head of the list, my removal code is a little bit more simple. So I know that I'm probably going to do something like this. But this definitely can't be the first thing I do. I definitely can't free the first item in the list because I'll lose the rest of the list immediately if I do that. So I want to be careful not to necessarily do that first. But what I want to do is I want the same kind of thing. If I want the first player to skip the second player, but I don't have a first player, then I will want the head to skip. So let's say I'm removing the first player, I want the head to skip the first player and go to the second player. And I can do that because I know the head is list. So I can say, list, you used to be the head of the list, but I'm moving you one further. So I'm going to say move that further along. And then remove the thing that I skipped, which was what the head had been pointed at previously. And I can't remove that if I've moved it along already. Show you an example of it. So let's get rid of that for the moment. And say my list pointer is aimed at the first element of the list. Miguel saying, yeah, I feel like a lot of tests and labs are too simple to be tested thoroughly. Yeah. So a lot of those, we're going to be quite lenient with things. Assignments are where we do serious testing to see if people are using other people's code. And in the exam, obviously, they're all big enough that we can really tell if people are working together or copying each other's work. So I've got my list pointer that points at the first one, and I know that this is the one that I want to remove. So if I want to remove this one, I want my list pointer to be aimed at this one. And I need to do that before I free this, because the only access I have to this one is to copy this. So the list pointer is going to copy this pointer from the insert position and end up pointed over here. The only problem if I do that, however, is then I've lost contact with this one, so I can't free it because I don't have a pointer to it. So what I will do first is I will make a new pointer. So I will make a new pointer, and let's just call that one removal node. And I'll make removal node a copy of the list pointer so that I have access to this one that I want to remove. Then I can copy the next pointer of list. So it's funny, list actually copies its own next pointer. And here, and so now list is pointed at the new head of the list, and the rest of the list moves on like that. But I have a pointer I've saved to this thing that I want to remove so that I can still free it. Again, all of these kinds of things, it's much easier to draw it first and think about the order that you want to do things. So, this is not the first thing I want to do. This was moving the green arrow to here. If I do that first, I lose this node. It becomes a memory leak. So before that, I want to save this rem node. So I'm going to make a new one. Removal node. And I'm going to say that's the head of the list. Because I know at this point, because I've done all these tests, if previous was null, it meant current was the head of the list. So my removal node is the head of the list. Then my head of the list moves to the second element. So I set up my removal node here. And then I've moved this from here to here, which means I can now free this node because it's no longer connected to anything. It's no longer the head of the list. It still has a pointer to the list, but that's fine because we've replaced it with a new head here. So I can remove this one now. So I'm freeing it there. So you can see how this all kind of has to happen in this order, or else our pointers are out of whack with each other. So, and I have moved my list to the new head of the list, so after I finish this if statement, I'll pop out here and I'll return the new head of the list. So what this should do now is take any name, any string that we type in, and what it will be able to do then is find whether that person is in the list, and then depending on where they are in the list, or whether they were in the list or not, it will remove them correctly. So we definitely need to test this now to see whether this is working. So, I wonder if we want to do the whole game loop now, or we could just at least do one test. Okay, so here we've put everyone in the list, and let's do one test. Yeah, I won't say pick. Please type in the name of a player to knock out, and then we'll fgets. If we want to fgets, we're going to need a string to put this in. So let's just do an input string. Ooh, max name length. Ah, beautiful. Max name length there, and we will fgets, and I will use my memory to see what fgets takes. Fgets takes in a string that it's going to write to, the maximum number of letters in that string, and the stream that it's coming from. So I know that the string is going to be this thing I've called input. The maximum number of letters is a handy hash define that I've got from previously. Where it's coming from the moment, standard input. Later on you will learn about how to do things like file input and other things like that, but for the moment we're going to use standard input. We know already that fgets is usually going to give us a the enter key, the new line that we type at the end of the line, so we need to remove that if we can. So let's look for it. So if the last letter of input, and the last letter of input is going to be the string length of input minus 1. So the string length will give us the number of items in input. I think I didn't do this in the example code, so I may change my slides later, on the slide code at least. So this says that the final letter of input, if the final letter of input is new line, so we have to do the minus 1, because if we did it just on this length of input, we would get the null terminator all the time, or the max name length, but I think there's fgets guarantees that will be the null terminator anyway. So I'm going to say 1 back into the list. Is that the new line? If it's the new line, then replace that letter. So I'm going to use the same letter, replace that letter with the null terminator. So if you remember, I think we did this previously when we were learning about fgets the first time. If we want to check for the final letter being a new line, we just find the index of the final letter, and then if it's a new line, we replace it with a null terminator. This is always pretty funny when we do this, right? Because we're doing all this stuff on linked lists, and I just go, oh yeah, we do arrays as well, and then we go back to linked lists, right? So what I'm hoping for eventually is that everyone gets comfortable with using both arrays and linked lists, and you can just throw them in amongst each other. Because when we're working with collections of data, like loosely connected collections of data, we're much more likely to be doing stuff like linked lists for them. But then when we use really constricted collections of data, and I'm going to say words, are very constricted collections of letters. You don't tend to insert letters into words or not, you tend to use them in chunks. Then they're always going to be in arrays. So we're going to be jumping back and forth between the data types like this. So my input is like that. Then I will attempt, I say attempt because we haven't tested this, I will attempt to remove player using that input. So I'm going to say the head is equal to, because remove player may change the head. So I'm going to trust that its output is the head of the list. So remove player from a list, and the list is the head, and the name I'm trying to remove is this input name that I've just read. In order to test whether that worked or not, I will also have to print players. Let's do another printf here, so that I'm just telling myself what's going on. The players remaining in the game are, I'll put a new line on the end of that one so that the list is all together. Izzy's asking, is it okay to have 2 null terminators in a row? Yeah, totally. The way that all the string functions work is they will read everything until they see a null terminator, then they'll stop. So the perfect string, if we have max name length, the perfect string is the letters that you want and then all null terminators, because that's the just in case string that is sure that no matter what you do, if you're skipping over letters, you'll always know when you've left the word and you're in that empty territory that's not meant to be used. So if we wanted to be really, really super safe about everything, when I declare this, I would then have a function that says prepare string or something that goes through and puts null terminators in every element of this character array. You will recognize this kind of thing from the first assignment, because in the first assignment we had an entire function that was said blank out the canvas. And I think the blanking out the canvas function, did we blank it to white or black? I think we blanked it to black, which meant that it would write 4s everywhere on the canvas. It's either 4s or 0s. I know it's one end of the scale. And so we were explicitly making sure that it was all on this kind of 0-ness. And if we wanted to be really, really careful with our strings, we would do that as well. We would say set everything up as the null terminator and then put your stuff in afterwards. Param has retracted messages. I assume that you were saying the same thing as me there. Anson's saying, can I explain the if condition again? So I'll show you. I'm going to make a new one here. So let us say, for example, I ran an fgets, and this is what I got. I typed in hello into the terminal and then pressed enter, and fgets put this into my string. So the length of my string is 1, 2, 3, 4, 5, 6. So Sterlen would be equal to 6. So if I put my indexes in here, 0, 1, 2, 3, 4, 5, 6. If I want to see whether there was a new line at the end of this word that I had just written, I need to check number 5. So string length of that string -1 is right here. So -1 from the length. The length is the number of characters. The length will be how many characters exist before the null terminator is seen. So if I do -1, I check this one, and I'm checking if it is a new line. So I'm saying, is that a new line? If it is a new line, I don't want this new line to be taking part in my string at all. So what I do is I overwrite the new line with a null terminator, which is going to shorten my string by 1 and make only these 5 characters here, the characters I'm actually going to use in the string. So Anson, hopefully that that shows you what we're doing here. So that we were doing this thing because we know that fgets is highly likely to add a new line on the end when I use it, and I'm just doing that little thing there to strip that new line off it. Okay, so I think at this point we're ready to test this for removal and see what happens. I'm going to reset this. This is like the autocomplete stuff. When its dictionary gets mixed up, it throws those little errors. I think this will work. Yeah, let's see. Do I have, yeah, previous compilation command. No syntax errors, that's not a guarantee, but we'll see what happens when we run it. Okay, so we've added everyone in there, and then we said, please type in the name of a player to knock out. So let's knock out someone in the middle of the list, make it easier for us. Chicken is literally knocked out. There. She's on this like little chair that I've put in here, like nearly specifically for her. So Chicken's literally knocked out because she's just asleep on a chair back there. So I'm going to knock her out first. Players remaining in the game are Ang, Katara, Mark, Zuko. Great. So we can see that my removal code has worked. So we can see that it was able to find Chicken. And if I wanted to I could put some testing code in here. So we know that I typed in Chicken, and this was able to loop through. Then current would have been pointing at Chicken, which means current wasn't null. Previous was not null because Chicken was in the list, in the middle of the list somewhere, so previous would have been Ang. Previous was not null, so the list then skipped over Chicken and then freed the memory, and we're out there. So that worked for something in the middle of the list. Let's run it again and try to remove the first and last elements of the list. This is how we do testing, right? We test lots of different situations and see if they work. Because we know that if I type in Ang here, I know that this is going to run a different bit of code. So we're going to get previous is null because we don't loop through the list at all. And so we have to test to see whether this code works. Remaining players in the game are here, so that's good. We know it's working to remove the head of the list, which was one of our conditions. Now we're going to remove... Let's remove Tom from the list. And it's like, wait, Tom's not even playing. That doesn't matter. I'm going to try to remove Tom from the list. The list remains the same. So I know that my code for looping all the way through the list and stopping at null is still returning the correct list. So this is the kind of thing that I will do to test whether my code is working. I'll test all these different things. You'll notice in assignment 2, we're asking you to write tests. This is the kind of thing we're asking you to do. Can you make sure that this function works under the many different conditions that it might be needed to work in? Okay, so I'm going to say for the moment, it's not 100% sure, but for the moment, things are reasonably working. We can make a list of players, we can make them in alphabetical order, we can remove a single player from the list, and now we can do the game code, which is remove players one at a time, and when there's only one player left, they're the winner of the game. So we're going to do this game loop. So what I'm going to do is start looping this. So what we'll do is we're going to remove a player, but then we're going to go back and remove a player again. I will just indent this correctly. Now, there are a few things going on here. So I'm going to call this the game loop. Keep looping until there's only one player left. Now, we've already got an issue here because I'm saying keep going till there's only one player left. At no point in this are we actually tracking how many players are in the game. So there's a couple of ways that we could do this. If we wanted to, we could just create an integer. So I could say something like int num players equals 0 to begin with. And every time I insert, I will add a player. And then every time I remove, I will reduce that. So I could do something like remove this num players minus minus. And I could do insert alpha num players plus plus, that kind of thing. You can already see the problem with this, right? You can see the problem with this because remove players doesn't always remove a player. We tested that, right? If you type in the player name wrong, then no one's going to get removed. So this is a shaky way of doing this. So I'm going to actually get rid of this immediately and say I don't want to do this because it's not entirely trustworthy. But I can think of something that I want to do though. So I could think of, I want a function that counts the number of players. So I want a function that's going to loop through the list, look at every player and add up the number of players. And then here's where I'm being tricky. I'm going to look at this function here and say this is a function that loops through all the players. It loops through all the players and then it prints them out. I'm going to get tricky and I'm going to double up with this function. So I'm going to change print players to an int function. I don't want to autocomplete that to int2. And this now will returns the number of players that were printed out. Yeah. See, I'm being tricky now. So I'm actually saying that every time I say who's still in the game, I will say how many of them there are, and I'll give that information back to the program for use. So I'm going to say int num players starts off at 0, and every time I print out someone's name, I say num players plus plus. When I've finished that loop, I will return the number of players. Cool. So what I can do now is every time I can print out the players, I can actually count how many times things are happening. So I'm going to actually remove this from inside the loop. I'm going to put it up here. Print players takes in the head. And I'm going to say if print players is greater than 1, then someone else will be knocked out. Shai said, make it so that if there's one player, it says winner, winner, chicken dinner. Okay, so winner, winner, we feed chicken dinner. We're not eating chicken, we're feeding chicken dinner. Because we would not eat her. She's way too cute. Okay, so we have... we know that when we exit the loop, there's one player remaining. Oh, there's actually one or less. If we run this without inserting any players into the list, then we're going to get a weird... It's going to look weird, like it's going to look like no one has won. But anyway, we'll print the players out, and the result of print players is how many players are left. So long as there's more than one player, then we'll try to remove someone. So we try to remove someone, we take the input, try to remove something, and we say the players remaining in the game are, and then we'll print the players. We don't necessarily want this to print out every time, because there's going to be one time in this loop where the game's going to end. So what I'm going to do is remove that, but we're going to put that into the print players function. So before we loop, we'll say the players remaining in the game are this. So every time we call print players, I'm going to remove this testing stuff that we had in here, where we're printing players every time we're adding players to our list. So this is our list of players at the moment. So we've got some fan favorites here in Avatar: The Last Airbender, and we have the lecturer in charge and me as the assistant lecturer for the course. Then we won't need to print them out here, because the first time we do anything, we will print out everyone who's in the game, and that will say, these are the people in the game, please type in the name of a player to knock out, and then we'll knock out players. But when there's one or less player remaining, we'll want to do something. So printf, what was it? Winner, winner, chicken's dinner. And we'll say that someone has won the game. So let's do a %s for a string there. Has won. And that string is going to be... Now we're making an assumption here, so I hope this is going to be okay. The head's name should be there. So this is bad if there's less than one player remaining. We can't just do head name. But we're just kind of assuming for the moment that we started with 5 and we went down to 1. And so we say they've won, and we end. Let's see if this works, though. Maybe sacrifice winner to chicken's dinner. There's been, I don't know how many horror movies there have been where cats eat people. I don't think there's been that many. There was one in New Zealand, which I thought was a really funny one, of like where the sheep were the horror creature. So sheep went kind of got genetically manipulated by some kind of virus and started eating people and things. I think that's quite funny. Okay, let's see this and see whether this... Oops, that's not reset. Let's see whether this is working. So we're going to compile this. And then run it. Okay, players in the game are these. Please type in the name of the player to knock out. Adam said Zuko needs to go first. So Zuko got knocked out first, and everybody's happy. So I'm happy now for people to... Oh, Shai said, does C have a random function? C does have a random function. We'll talk about that in a second. We're not going to have time to implement it, but we'll talk about it. The randomness I'm going to use is chat. So type in a name in chat for who's going to... Oh, Katara. Sean called that one. So Katara got knocked out next. Okay. Now who's next? Anson, knock everyone out except for Chicken. Daryl has called me. So Daryl, I am going to look up your name in 1511 and reduce all your marks to 0. And Miguel says Ang goes next. Look, I'm doing pretty well here, because every time I have done this kind of example before, where we remove people, I have been the first to be removed every single time. So this is like the one term ever that I haven't, they haven't just been knocked out first round in my own game. And then we see the players remaining in the game are Chicken, winner, winner, chicken's dinner, chicken has won. Which is correct. Sean says Mark should have won, give me extra marks. Yeah, okay. So this is cool, right? So what we've got here, so we've spent 3 lectures on this, and we've put together this entire program that's able to do all this kind of stuff. I would actually potentially think about putting this in a separate function, which is like run game now. See you, Miguel. Wait, isn't it? Like, it wouldn't be on for another 10 minutes. Anyway, you can go whenever you need to go. I would potentially think about putting the game loop in a separate function, so you just have insert these things, then run the game loop. But it's okay, I'm going to leave it there as is. So let's look back over what we've created here. We have made a structure that is a linked list piece. And then we've said we've got a way of making an individual player by assigning them their name and then whatever next they've been given. So that was just like a tool that we use to make players. We're very rarely going to use this in our main because it's not complete, because we need to provide it a next pointer and things, but it is going to get used inside other things. We had a way of printing out the list as well, which we've seen. We've just edited that recently. Insert after says if we have a position, we can put a new player in afterwards. That was making use of the create player, and it needed a pointer for an insert position. So now that we're using this insert position, we could insert alpha by looping through the list, looking for the right position and inserting it. And then we added the ability to remove player, which was similar. It was looping through the list, looking for where to remove the player, and then it was pulling something out. So we're pretty good, right? We've got this whole thing going, and we think that we've probably got everything working. So let's run this now with leak check. So leak check is going to tell us if we've left any memory behind or anything. So quickly in chat, fire off who is going to get removed from the game, and I will remove them in the order that they come in chat. This I will laugh if I go first, because I think that might happen. Yep, I thought that might happen. Thank you, Josh. I appreciate your support, and Gordon. All right, now you have to put other names in now, everyone. Ang goes next. Wow, this is in power order, so we're going from the most powerful to the least powerful. Sean, unpopular decision. Chicken goes next. It's between Zuko and Katara. Very interesting. Param said Zuko, so Zuko goes next. Katara wins. That's cool, because Katara is really cool, so it's cool that she can win. However, error. Free not called for memory allocated with malloc in function create player in Battle Royale C at line 63. So line 63. Somewhere we have allocated a player that has not been cleaned up correctly, and we know this because Katara is still in the list and has won. So we know that we're not cleaning up what we're doing. So let's have a look at that. Cleaning up, so we, as I said here, we can run leak check to see whether we've freed memory or not. So let's write a function that's not just going to like assume that there's only one person left. Let's write a function that does clean up the entire list. So we have to be careful when we're looping through this list, and we saw this already when we were I've already wiped it. It's alright, I've wiped our virtual whiteboard. We've seen this already, that when we move a loop pointer along, we want to carry, in a sense, a pointer to the previous node. So when we're going to loop through a list and we're going to free them all, we want to move the loop pointer onto like the next node in the list and keep the previous node in the list, then free this one. So we free this one, but we've still got access to this next node. And then we will move the loop pointer along again. Sorry, I don't have more diagrams of the same thing. The loop pointer will move along again. The free node pointer will come to this one and we'll free it. So this way we're going to go through the list and we're going to eat up all of the elements of the list and free them. Code's going to look a little bit like this. It's actually quite simple, but let's make it instead, because we want this program to be absolutely complete when we finish, which is going to be in the next 5 minutes. I'm going to call it free player list. And we are going to get a pointer to the list. We're down here at the end. Loop through the list, freeing all the player nodes. Okay, so we know we're looping through the list, which means one thing that's interesting. I'm going to say that this is the time we don't need to do this. Because when you think about it, if we're going to destroy this entire list, then we don't care what happens to this list pointer. We're not worried about the head of the list anymore, because there should be no list after we're done. So we're just going to use the list pointer. So while... we're going to loop through the whole list. So you can see sometimes when I'm making a loop, I will go all in the beginning and say, I'm just going to do a bog standard loop first, and then I'll think about what I'm doing afterwards. So what I'm going to do is I'm going to move these pointers along, and I'm going to remove the previous elements of the list. So I'm going to make a pointer in here that's a player pointer, and I'm going to call that remove node. And it's the same kind of thing as this one, where I'm going to have a remove node that points at the current head of the list, then I'm going to move the head along, then free the previous one. This is actually the same thing that I'm going to do, but this time I'm going to loop it all the way through the list, and I'm going to remove the head of the list every time. So I have the removal node is equal to the list node. I could have called this, you know what, I'm going to change this to the head. So it's clear that I'm looking at the head of the list here, not thinking of it as the entire list. But I mean, when you think about it, the head of the list is access to the entire list. Indirectly, but it still is. But I'm going to say this is specifically looking at the head of the list. So I'll go back up to the top and say this looks at, give me the head of the list and I will remove it for you. So if the head wasn't null, then put a pointer to the head saying that this is the thing that's going to be removed, then move the head pointer along because there's going to be a new head of the list, because I'm just about to free the rem node. So what this is going to do is it's going to say that, let's draw it. So my head pointer starts here, and I'm going to say make a new one called rem node, and that copies the head pointer, and then the head pointer moves on. Head pointer moves on there, and then we free the rem node. So we free this. And then we loop. Head wasn't null. So if head wasn't null, we'll copy the head pointer in rem node, which is this line. We'll make a new rem node actually every time, which is fine. And then we'll say the head moves on to the next one. Which moves this on here. And then we see we'll free whatever rem node is pointing at, which is this one. So we say, you go away. And so on until the head points at null. And when the head points at null, then we know that we've removed all the nodes from the list. So we can go back to our main function after our game is finished. We can call free player list on the head, and it doesn't matter how this finished, whether it was one player or many players in the list, we will have removed them all, and we've cleaned up all our memory after ourselves. So this is a really, really simple function that is going to loop through a linked list and remove all the memory. Oops, I didn't need to alt tab that. So let's compile this with leak check again. Start typing in names now. So that we can do this quickly, because we've reached the end of the time here. Who's going to get knocked out first? Oh, people don't like Zuko. That's fine. That's fine. Then Aang. Oh, we're getting rid of all the benders first, are we? Gira-chan wants to go next, so Oh, strangely enough, everyone's still there. Chicken went next. Oh, it's between me and Katara. What a tough call. Katara! Mark gets to win! Winner winner chicken dinner. Mark has won, of course, because Mark is the one that feeds chicken dinner. So it makes a lot of sense. And notice now, leak check is not complaining anymore. Shy says Mark just codes her out of the game. So, leak check is not complaining anymore because we have freed the list. We've freed me after I've won. So that's nice. Oh, very gladiator. So now we have everything. So we've made a complete linked list program. We've created nodes. We've been able to loop through them. We've found insertion and removal, and we're managing our memory completely. So, challenge before we finish, because I'm already a bit over time. Look up the function rand and srand. Srand's not entirely necessary, but srand helps to make sure your game doesn't run exactly the same every time. But rand will generate a random number. I'm going to say random in quotes because it's not entirely random. Computers are deterministic, but it'll appear random to us as humans. If we want to remove something from a list randomly, if we know how many things there are in the list, we can generate a random number, which is like a random integer, so it could be massive. We could use mod to push that into the list, and we've done this kind of thing before with our dice checker, I think it was, our very first dice thing. We used mod to move a big random number into a number in the list, and then we could loop through our linked list exactly that number of times, pick a person and remove them. So you can try that if you want to. That's a way that we could remove a specific number position in the list. This might actually be useful for the assignment as well. We don't have random in the assignment, but we do have the idea of looping a certain number of times and then doing something. Zeal has some code there. YouTube tried to stop you from doing that because it looked like random stuff. So I'm not sure exactly what that code is that you're doing there, but yes. That is a lot of stuff that you can show to use the random functions there. So you've obviously used them before, I think. Okay, so we've got to wrap it up there. I'm a bit over time. So I will pause where we are there. And I'll come back for Q&A afterwards if anyone wants to talk more about what we've done in the linked list thing or ask questions to clarify. I'll be back in a few minutes. But that is the end of the official lecture. Thanks, everyone. And hopefully, with this big example that I've done here, it's giving you a lot of potential starting points for the assignment. So several of the different stages of the assignment are covered a little bit in this example. None of them are covered, I think, in their entirety, but they'll be covered a little bit so that you can use some of this code to kickstart what you want to do in your assignment. Thank you, Gira-chan. I feel very proud of my win today. Okay, I'll be back in a sec. Alrighty, I'm back. I'll go back to the code screen because I'm pretty sure the code screen is the thing that people are going to want to look at. That's a lot of code. What are we at here? I don't need the white space anymore. 180 lines of code. I mean, it's not an assignment. But there's probably more in this example than anything else we've done in 1511, which kind of makes sense, because this is, I guess I would consider this the capstone of what we do in 1511. This is like pinning together the entire second half of the course and leveraging your understanding of everything we've done up until this point. So it's got everything. It includes, it's even got a constant, it's got structs, it's got pointers, it's got linked lists, it's got some complex use of functions as well. So there's heaps of stuff going on here, which is really cool. Does anyone have any questions that you would like me to clarify further what I'm doing here, or pick at a particular part of this and you want me to go through and maybe draw a diagram, show how it works, or anything like that? Let me know in the chat now, and then we can go through and look in more detail. But we're never going to run it again because I won, so I'm retiring as the champion. It's okay, we can run it again if we want to test stuff. So Param's asking, in the remove player function, can't we just use the current variable instead of remnode? Because it points to the head when we remove the first name in the list. Yes, you are correct in that remnode was unnecessary. I didn't need to make a new one, because if we're at this point, we found a match. So yes, we don't need a remnode. I think I did remnode because I was instinctively writing this code, where that wasn't necessary because we already had a pointer to the head of the list. So yeah, I'm happy to edit this. So current is pointed at the thing we're going to remove, and we do need to move the head of the list to the next at the head of the list, but we're freeing the current. Interesting, here we now have repeated code. If we have repeated code, we don't necessarily need to have it in both forks of the program. So it's like, if it's null, we do something. If it's not null, we do something else. We do the same thing at the end of both. So this is nice, Param. Nice spot, because now instead we can say that, oops, lots of indentation, no matter whether it's the head of the list or another element of the list, it's going to get freed. The only difference is how we prep what we're doing. So one of them is to move the head of the list along, or if it's another element of the list, we skip it using the previous node. So either we're skipping the head node over, or we're skipping the previous over. To make this more consistent and more readable, I might even do this. The list, I don't know if that's actually more readable, because list and current are both pointing at the same thing here, so I could use either one. But I'm going to say list is list next, to say that the head moves one along. This one is previous is current next, because we're skipping over current specifically. And then free current comes here, which is nice. So we know that if the current wasn't null, no matter what we do, we're always going to free that one. So that's a nice spot. That actually smooths out the code a little bit more here. And I'm pretty sure is the code that's in the slides. But I don't like to look at the slides when I'm coding live for you, because if I do that, then I won't necessarily talk through the process of creating it. I'll just be writing down what's on the slides, which is super boring. So I don't want to do that. So the slides are there for reference, but it won't always be the same code, because I like to actually show the code being created out of a human brain rather than off a slide. Any other questions anyone has? This is unexpected. Usually when I do this much difficult code, I expect more people to be saying, I'm not sure what's going on here. So I'm obviously going to take that as a win, that I have obviously explained things so well that people didn't need to ask any questions. The other option, which is the opposite option, which could be bad, is that whatchamacallit, that everyone doesn't understand what's going on to the point where they can't ask questions. Yeah, apparently we had a few less people than normal today. So our like maximum was 80 at some point. Having said that, it's not that much different. I think in person at the moment is hovering around 100. And there's heaps more people just viewing things after the fact, which is fine. So long as you do watch it eventually when you need it, then that's okay. Trent has a question. Why is the if condition regarding the input necessary? Isn't the second last character always going to be changed? Okay. Where's the input? So, you'll notice that I made the same assumption in the slides. Where are they? Here. So I said character KO name, fgets, and just remove it like this. So I actually wrote these slides before I had a deeper think about what was going on with fgets. So fgets will say, I will put a null terminator at the end of max name length. So the largest number string that you can type in is max name length -1. So if we look at our code here, and max name length is 100. If I type in a word that has more than 100 characters, so it's a little bit far-fetched for this example, because none of these names are over 100 characters. But if I type in more than 100 characters, it will not read any characters I type in after the 99th. It'll say, no, you told me that this was the maximum number of characters you were going to give me. So I'm simply going to stop reading after a certain number of characters. In which case, the last character in this string will be a letter that I typed in. It won't necessarily be the new line at the end. So on that very edgy edge case, like the most edgy of edge cases that will probably never happen, there won't be a new line at the end. There'll be a letter. And so I'm testing for that just in case. Because we can't guarantee that the last letter is a new line, and we might just be stripping a character off someone's name. The worst case, if someone's name is exactly 99 characters long, I mean, this probably wouldn't happen, but if they were exactly 99 characters long, and the new line wasn't read in by the fgets, but all the other letters are correct, all I'd be doing was to be stripping the last letter from someone's name. This is something that would be much more likely to be a problem if this was something like this. If max name length was really short, there'd be a chance that people would be really close to that max name length. When it's 100, we're reasonably safe with all of these really short names. But I want us to get in the habit of using this so that we don't always assume that the new line is the last character in an fgets, because there's always a chance that it might not be. Yeah, you were thinking that already. Yeah, totally. Yep. Okay. I will just wait a moment and see if there are any other final questions, but it looks like everyone's thirst for knowledge is sated for the moment. And there's a lot that you can work on now with this example. Obviously, I will upload this example in a moment. I'll just see if there's anything else I need to change in it or comments that I need to put in to explain things. But I think it's pretty good for the moment. And I think for a lot of people, this might be the reference code that you use to start the assignment, which is fine. You know, I'm happy for it to be that because that's why I'm doing it. Yeah. All right. I think we have run out of questions for today. Good luck, everyone, and remember that if you need help, spare time in labs is the first thing that I would do for help, because you've got a decent chance of getting one-on-one help there. Help sessions are also one-on-one help, but there's a queue for them, so the closer you go to the due date, in any of these things, the closer you go to the due date for help, the more flooded our staff will be to help you. So just always take that into account. Starting early is always going to be easier than starting later. I always laugh whenever I say that because, you know, I was a student as well, and I also probably ignored that advice too much. But you know it's going to be better if you start sooner. You've been there before as well. I know it. Oh yeah, so labs first, help sessions, then forums. That's a good order to go for help if you need help in the assignment, because I think the best help that you can get is interactive help. So go for that first. Okay, see you all soon. See you on Tuesday. Next week we will be delving into some slightly more arcane topics. So we're going to be looking at weirder stuff that is potentially harder to understand, but also very interesting in some very, very cool and strange ways. So we'll look at that. So next week is stuff that's not really going to be that accessible in the course, because like if you look at our structure, it's like lecture, lab, then weekly test. So next week is where we start doing things that we won't have in weekly tests. So it's going to be less assessed. But I think it's still some interesting stuff. So see you soon, and see you next Tuesday, and good luck with your assignments.